It's space weather. Yes, indeed, weather from space. The space weather. Earth is a cosmogenic place. Got the sun on 171 angstroms. Sunspot 2729 ain't going away anytime soon. I think it might have actually grown bigger there at the end. Let's take a look at it in 304 angstroms. Some filamentary activity toward the south again. Zoom in on that sunspot. And let's head to Solar Ham real quick. And indeed, it hasn't increased to a different class or anything like that. It does look a little bigger than it was yesterday. And there's some significant field mixing going on in there. Check that out. Get close up. Yeah, there's some significant mixing. So we'll be watching that closely. And let's look at 193 angstroms. Check out the coronal hole situation as a new one has formed. It's very small and very defined. And your magnetic lines are somewhere. There we are. That coronal hole is looking quite strong yet. I mean, the length of these lines here, I mean, they're not strong enough to mask this sunspot. You know, sometimes we get coronal hole fields that are in the way of a sunspot and you can barely see it on this view. But it is a very strong field. And I see some increased activity right here also. And let's look at spaceweathernews.com. Sun is at a very low level of activity, but there's a slight ramp up. So X-ray flux is still flatlined. Surprisingly, no other X-rays. And we have it just in the last couple hours here. We've got a complete shift in the BTBZ and in the phi angle. So perhaps a coronal hole magnetic disconnection at the same time as a coronal hole wind stream arrives. You can see the density is ramping up, and actually the speed's ramping up at the same time, so that's interesting. We got to keep an eye on that one there. No prediction shall be offered. Now, the magnetometer is looking extremely steep and spiked. We had this double drop off here. And so that's something to keep an eye on also. And the KP index is all the way up to 3. Interesting. We are seeing an electron flux dip as we usually do with coronal hole wind streams. And the F2 ionosphere layer is looking a little on the discharged side considering how high the KP is. So this is trying to reach equilibrium. And frankly, the southern hemisphere looks a little overcharged. But in any case, and that's your space weather information. Now, who's ever heard of Milankovitch cycles? Actually, before we do that, let's cover earthquakes. For the past 24 hours, as the South Pacific is rocking again. So, let's see, what do we have here? Alaska getting hit repeatedly with small quakes. most around the 2.5 to 4 range. Nicaragua gets a deep quake, which puts them on alert for a slightly larger surface quake. The Banda Sea. Not familiar with that one. Let's take a look at it on the map. Oh yeah, by Indonesia. No surprise there. Alright. And it's taken forever. Anchorage got another 4.8. See if I can get to where we were here. Jeez. So 5.3 in the Philippines at depth. Philippines stays on alert. 5.0 in New Caledonia, 4.9 in New Caledonia, 5.0 in New Caledonia. That's a lot of quakes in the South Pacific. Vanuatu, 4.8 in Anchorage, 5.7 in New Caledonia, and a 4.9 in New Caledonia. 4.5 in Peru. Peru should be on alert for a 5. 4.6 for Indonesia, 5.0 in New Caledonia. Tonga gets a 5.3. And that's the earthquakes. Now, back to Milankovitch cycles. Who's ever heard of Milankovitch cycles? Milankovitch cycles are the primary driver of the Earth's climate. And there's a bunch of different factors that cause these. A bunch of different waveforms that kind of interact with each other. We will leave links to this article below. But what we want to show is how the Milankovitch cycles relate to Earth's climate. So let's just look at the past, I don't know, what, 600 million years? 542 million years? And so keep in mind this graph zooms in and out. So you got to keep track of the time scale at the bottom there. Now, for anybody suggesting that, last year was the hottest year ever, you may want to show them this graph, because we've got some much hotter temperatures here that were 6 degrees C warmer than it is now. Also, it may be interesting to inform them that Antarctica started to form about 33 million years ago, when it was 3 degrees C warmer than it is today. It also may be interesting to know that if you look at the last 500,000 years, this little zoom in here, this spot right here, those are the Milankovitch cycles. Now, why is that important? Well, because this pane is just a zoom in of one of these Milankovitch cycles, which comprises all of human history. Now, if you look at how tenuous the temperature is, see that? Those are the warm periods over the last few Milankovitch cycles. Where's most of the data? Down here. Because the Earth has been an ice planet for the last probably something like 30 million years. And so the normal state of affairs is frozen. So let that sink in as we move on to our next slide. Svensmark. So we headed to drtimball.com, and it's an article from 2014 regarding Svensmark's cosmic ray theory. Swedish physicist proposed that perhaps cosmic ray flux is associated with cloud cover, suggesting that, greenhouse gases such as, man-made CO2 and also real greenhouse gases such as methane while they may contribute to like cloud nucleation, what about cosmic rays? We know that cosmic ray flux increases when solar activity drops. So great flow chart here. Lower magnetic field strength, fewer sunspots, less solar wind, more galactic cosmic rays. Now the sun puts out cosmic rays also. More low-level cloud formation like stratocumulus clouds, cirrostratus clouds that you see in the top and in the lower 15,000 feet of the troposphere. More sunlight reflected into the space, aka increased albedo effect, and the Earth becomes cooler. Essentially, Svensmark's theory is not that the climate causes clouds. The theory is that clouds cause the climate. Cosmic rays cause the clouds. Here's a little simple example diagram here. Cosmic rays come in. They are split into different particles. They create electromagnetic fields. Electrons are set free when they smash into things. You know, solar protons really, really want an electron. And so they cause ionization paths on which clouds form. And we look at these daily. We'll leave links to the article. It's a bit on the old side, but it's still relevant today, especially when people are still trying to tell you the planet is warming and that human CO2 emissions are causing it. Next, let's look at a quick electroverse.net article about Professor Valentina Zarkova's recent talk in October, where she's predicting a super grand solar minimum based on study of the sun's internal magnetic dynamos. It's a short article, but it does have links to the full talk, and we will leave links to that below. It's actually posted November 6, 2018. And if you're not aware of what we expect for cycle 25 and 26, you should probably listen. Her models have been 93% accurate. The most recent one was, I believe, 97% accurate. And so the magnetic fields of the sun are going out of phase. Here's a video from one of our officially endorsed channels, Oppenheimer Ranch Project, where he's interviewing inventor Lee Wheelbarger. And there's a quick graph that you can see of the predictions of how weak the upcoming solar cycles are predicted to be. When we start talking about cycle 25, people are going to get all up in arms and they're going to get mad. And they're going to talk about whether the cycle's begun or not yet, reverse polarity sunspots, and so on. We're not going to do anything about that. But I would like to direct you in, trying to help people further understand the sun. I would like to direct you to rexresearch.com. Links to this article also regarding David LaPointe's Primer field theory experiments. Super interesting plasma experiments. Totally different than the Sapphire Project, but still making plasma. And ultimately, that is the structure of the sun. Now, David LaPointe will argue that's the structure of all matter, and perhaps he's right, but we're only particularly interested in the sun. This is the way the fields are going to propagate. Right here. I mean, in this situation, the planetary disk would be like this, and all the planets will be aligned on that planetary disk. The heliospheric current sheet is like this. And you are here. And let's just close things out by looking at a nice shortwave shortwave IR radiation map. Thanks to the NASA GOES interactive weather satellites. Thanks everybody for watching. We'll be doing it all again tomorrow. Remember, when you're looking at the real science, don't drink. And if you drink, don't drive.